Hi and welcome to linear algebra. So let's start at first with the first part, chapter 1, where we're going to introduce vectors. So what is a vector? A vector is a quantity that has magnitude, which is size or length, and direction or heading. The difference with scalars is that a scalar only has a magnitude while a vector indicates a direction as well. For example, velocity or force direction. Geometric representation as an arrow in space, we have the length of the arrow is equivalent to the magnitude on an axis system, and the arrowhead represents the direction. Algebraic representation, for 2D vectors, you have two coordinates. V has Vx and Vy, which are like x and y. Okay, these are the coordinates of the head of the vector, okay, the second tip of the vector, while the first tip is sprouting from the origin of the axis. As for 3D vectors, we have Vx, Vy, Vz, okay, Vz. So three coordinates for length, breadth, and height. N-dimensional vector, you would have V1, V2, Vn, etc. for multiple dimensions. Types of vectors, so you have the generic types are zero vector that has a value of 0, unit vector which is has a length of 1. It would be the vector, okay, equivalent to the length of each section, okay, of each division within the axis system. Equal vectors are vectors that not only have the same magnitude, the same length, but also have the same direction, heading to the same place, okay? So they are parallel vectors, but at the same time, they have the same size or magnitude. Now, negative of a vector is a vector which has a completely opposite direction, but the same magnitude, okay? So you would have a vector like this, and the negative one is the one going completely the opposite way. Free versus bound vectors, free equal position irrelevant, okay? So it has nothing to do with position, or its position is irrelevant. Bound vector, it means that it is fixed at a start point, but it can go at different directions. So to give you an example, let's say we're talking about negative or negative of a vector. So let's say you have a vector like this. Its negative is the opposite vector having the same magnitude but a completely inverted direction. Now, free vector would be like this, okay? It can go anywhere. Free, so the position of it is irrelevant. However, a bound vector has the same origin, so it would change directions, okay? But it is always fixed at the same originating point. Okay, hope this clears it out. Magnitude. So what is the magnitude or the size of a vector? How to get the magnitude? Formula in 2D is given by V in absolute value, or the size of V, okay, magnitude of V is equal to square root of Vx squared plus Vy squared. So it is the square root of the sum of the squares of different coordinates. Okay, so in 3D it becomes square root of Vx squared plus Vy squared plus Vz squared. It has the same, formula, follows the same pattern. So in n-dimensional case scenario, V becomes, okay, or the size of V becomes equal to the square root of sum of different coordinates, all of them squared. So sum of Vi squared for I starting from 1 all the way to n, or in other words, square root of Vx squared plus Vy squared plus Vz squared plus Vt squared, etc. Direction of vector. Now, the unit vector in the direction of V is given by V hat is equal to V, the vector, okay, divided by what? The size of V. Okay, so it is V divided by the size of V. Vector addition. So what is the definition for that? Adding two vectors produces a new vector by adding their components. So U plus V, okay, which is the sum of two vectors, is equal to u1 plus v1, u2 plus v2, all the way un plus vn, meaning that, let's say you have u having coordinates x, y, z, v, x prime, y prime, z prime, okay, so u plus v would become a vector of the following coordinates, x plus x prime for the x coordinate, y plus y prime for y, and z plus z prime for z coordinate, okay? Or in other words, let's say you have u with coordinates ux, uy, uz, v with vx, vy, vz. So u plus v gives us ux plus vx, uy plus vy, uz plus vz. Geometrically, you place the tail of v at the tip, at the end point of u, okay? So the head arrow of u, this is where you place the starting point of v, okay? The tail of v. And the sum is from the tail of u to the tip of v. Using the parallelogram method, okay, you place both vectors at a common origin. The diagonal is the sum, okay? So the sum would be the diagonal of the two vectors. To give you a more graphic illustration, so let's say this is u. So v should be placed at the tip, okay, the tail of v, starting point of v should be placed at the head of the arrow u, and the sum of the two vectors becomes, you know, this diagonal, okay, of the parallelogram. I'm trying to draw it, which is this one. This becomes, you know, the sum of the two. So why is that? I'm trying to get a better color. Okay, so this would be w, the sum of the two vectors. And why I'm saying the parallelogram, because you need to, you know, continue this drawing of the parallelogram to figure out what I'm referring to. This is how you get w, or like the resulting vector, or the sum of u plus v. Okay, you have now, what are the different properties of the sum? So this is w, okay, assuming that this is a perfect real parallelogram, although it's not perfectly drawn, okay, but you get the point. So w, which is the sum of u plus v, is the diagonal of the parallelogram formed by u and v. Now, what are the properties of the sum, or the addition of vectors? First of all, it's commutative, meaning that u plus v is equal to v plus u. Associative, so u plus v plus w is equivalent to u plus v plus w is also equal to u plus w plus on the outside v. So it's associative, no problem in that. Additive identity, meaning v plus 0 is equal to v. Additive inverse, meaning that v plus minus v, when you add a vector to its inverse, it gives you back 0. Scalar multiplication. Multiplying a vector by a scalar k scales its magnitude without changing the direction, unless k is less than 0. In such case, it reverses the direction of that vector. So k times v is equal to kv1, kv2, kv3. So you multiply all of the coordinates by the scalar k. Now, the geometric effect. If k is greater than 0, the vector stretches, okay? It becomes lengthier. If k is between 0 and 1, the vector shrinks, okay? So it becomes a smaller size of its original, okay? So you are shrinking it down. If k is negative, then the vector reverses direction, okay, and the scales at the same time. Properties: distributive over vector addition, so k times u plus v is equal ku plus kv. Distributive over scalar addition, so k plus m times v is equal kv plus mv. Associative with scalars, so kmv is equal to km times v, with k and m being constant, and v is the vector. And you have multiplicative identity, which is 1 times v is equal v. Vectors in 2D. The visual model, okay, for a vector in 2D is a directed arrow in a flat plane The tail of that vector starting point, in other words, often is the origin of the axis, which is at 0, 0. As for the head or the tip of the vector, in other words, the endpoint, this is the head for which you have the coordinates Vx and Vy. Okay, so when you see a vector with Vx and Vy, these are the coordinates of the tip or the head of the arrow. As for the magnitude, as we've seen before, it is the length which is designated by V. An absolute value is equal to square root of Vx squared plus Vy squared. If it's in 3D, the same thing, except you add Vz squared. Direction, which is the angle of the vector, is given by theta, is equal to tan tangent, okay, the inverse of the tangent of Vy divided by Vx. Okay, so as an example, let's say you have V vector is equal to 3, 4. It's a vector pointing 53.13 degrees above the x-axis with length 5. Now, addition to the tip to tail or parallelogram method works directly in the plane. Now, let me talk about something important here. Okay, so how did we get the angle and the magnitude? So you have, this is the arrow here. Let's say this is the arrow. Or should I erase it completely and switch the color into red? Okay. So this is the arrow. This is the axis system, okay, the XY system. Now the arrow, the tip of the arrow has coordinates X, Y, correct? So this is X. And this is Y, the Y coordinate. Notice something that the length, okay, here you can apply Pythagoras method, which is the length of this, okay, which is a rectangular triangle. So the length of this here, which is the hypotenuse, which is at the same time our own vector. Its length is equal to square root of x squared plus y squared, correct? Actually, the Pythagoras formula is L squared, or the hypotenuse square, is equal to length square, length of or the first side of the triangle, okay, square plus width. This is width would be y, okay, width square. Or in other words, okay, so let's write it also in another format, which is, okay, so the hypotenuse square, which is at the same time, this is the length of the vector, is equal to x squared plus y squared, correct? The length of the two sides of this triangle, okay, this is the triangle here. So h squared is equal x squared plus y squared. Hence, h would be equal to square root of x squared plus y squared. In other words, this is how we've gotten v. The length of the vector is equal to square root of vx squared, which is the first coordinate of the vector, plus vy squared. Now, as for the angle of the triangle, okay, so how do we get the angle? Again, this is the vector here, v having x and y, okay, coordinates. I'm sorry, let me try it all over again. So yeah, this is x and y axis, and this is the vector. I will draw it in a completely different color. So this is the vector v. Now, how to get the angle? So v has vx and vy, remember, okay? Vy and vx are the coordinates. Okay, now remember that this is theta, the angle for v formed between v, the vector, and the x-axis. So tan theta, going back to trigonometry, is equal to, you know, the opposing side of the triangle divided by the adjacent side, okay? So it would be this opposing side, which is Vy, divided by adjacent side, which is Vx. So theta would become arctan or tan minus 1 of Vy divided by Vx. This is how you get the angle. Okay? This is how we've gotten different measurements, and the most important ones basically, which are the magnitude and the direction. Vectors in 3D, visual model. Okay, directed arrow in 3D space. Think of X, Y, Z axis. So instead of a flat 2D surface, you have it in 3D. It's sprouting in a 3D environment. Okay, so the tail usually starts at origin 0, 0, 0. Head has the coordinates Vx, Vy, Vz. The magnitude is V is equal to square root of Vx squared plus Vy squared plus Vz squared. Direction expressed using direction cosines or spherical coordinates. The direction cosines are the following. So cosine alpha is equal to Vx over V in absolute value, or the length of V. Cosinus beta is equal to Vy over V. Cosinus gamma is equal to Vz over V. As an example, it's like, the unitary vector here, except you have cosine alpha, beta, gamma. So let's say V is equal to 2 minus 1, 2 is a vector of length 3 pointing toward the octant, okay, where x is greater than 0, y less than 0, z greater than 0. Addition in 3D, same tip to tail logic, but in the 3-dimensional space. Parallelepiped visualization. Dot product or inner product, okay, for two vectors in R, and A dot B is equal to sigma AI BI, okay, AI BI being the coordinates of the respective vectors A and B. In the geometric form, and we will give an example for that, A dot B is equal to A, which is the length of A times the length of B times cosine theta, which is the angle formed between A and B. Key properties, okay, so the result is a scalar value, not a vector. Commutative, so A dot B is equal B dot A. Positive definiteness, so A dot A greater than or equal to 0 only for the 0 vector, measures parallelism between vectors, okay? So mainly, if A and B are two perpendicular vectors, if they are orthogonal, then A dot B would give you 0. Okay, so let's say you have two vectors, U and V. U dot V gives us Ux Vx, okay, so x of U times x of V plus Uy Vy plus Uz Vz. So plus Uz Vz, or Z of U times Z of V. This is how we get the dot product. Cross product. Okay, so what is cross product? You have A cross B, and this is how we evaluated the same method of evaluating a determinant within a matrix. Okay, the matrix is a multi-dimensional vector. Okay, so A cross B is equal to, you place I, J, K, which are the three components for a 3D vector here, okay? Like these are the three unitary vectors for X, Y, and Z of the two vectors A and B. Then underneath them, you have the coordinates of the first vector, which is A, designated by A1, A2, A3, or in other words, AX, AY, AZ, the same thing. And B1, B2, B3 for B. And this is how we evaluate it. So you place at first I, and you multiply it by A2, B3 minus B2, A3. Okay? So this, the product of this, minus the product of this. Then, when you get to the middle, okay, here we need to flip J to minus J. It's always the case. Okay? So minus J times, and you open the parentheses. Okay, so we establish the intersection between the column of J and the column, and the line of J. So the line and the column that are intersecting at J. So you get, what remains is A1, A3, B1, B3, okay? So minus J times A1, B3 minus B1, A3, okay? This is how we get it. What remains is K. Now here, okay, so always you have the signs are plus, minus, plus. So we've started with I multiplied by, okay, so what are the two column and lines, the rows intersecting at I? These are the column and line. What remains is A2, B3 minus B2, A3. A2, B3 minus B2, A3. Then after that, you have J, okay, so under with J, okay, over J you place minus, so minus J, and these are the intersecting lines and line and column, minus J times A1, B3 minus B1, A3. A1, B3 minus B1, A3, plus finally K, okay, so K here should remain positive. What are the intersecting line or row and column? They are the following. So plus K times A1, B2 minus B1, A2. A1, B2 minus B1, A2. Okay, the geometric form is the following. A cross B is equal to A times B, and the length of A times the length of B times sine theta instead of cosine theta. The direction of this vector, which is the result of multiplying, cross multiplication of A and B, is actually what? Perpendicular, okay, it's orthogonal to both A and B. To the plane, it's orthogonal to the plane where A and B reside, okay? Because when you have two vectors, there would always exist a plane where A and B coexist on that same plane. So this cross product is actually A cross B. Okay, this cross product is a vector that is orthogonal, having an angle of 90 degrees, okay, forming an angle of 90 degrees with both A and B at the same time, or with the plane encompassing A and B. The magnitude, now this is the interesting part. The magnitude for that vector, for that cross product vector, and by the way, unlike dot product, the cross product generates a vector, not a scalar. So the magnitude of A cross B, the magnitude for that vector is actually the area of the parallelogram that is formed between these two vectors. Key properties, result, so the result is a vector, not a scalar. Anti-commutative, so A cross B is equal to minus B cross A. It's not the same thing. And orthogonal to both operands, so U, V, you have U with Ux, Uy, Uz, V with Vx, Vy, Vz. Okay, U cross V gives us Ijk, Ux, Uy, Uz, Vx, Vy, Vz is equal to, again, I multiplied by Ux, Vz, I multiplied by Uy, Vz minus Vy, Uz. Then here you have a minus sign, minus J multiplied by Ux, Vz, correct, minus Vx, Uz, Ux, Vz minus Ux, Vz. Finally, K, here you got the plus sign, okay, only minus in the middle, so here the plus sign remains plus for K. So K times Ux, Vy minus Vx, Uy. Okay, so Ux, Vy minus Vx, Uy. Two vectors U, V within R are orthogonal if U dot v is equal to 0. This means in such case that the angle theta between them satisfies cosine theta equals 0. Correct? In other words, theta would be 90 degrees, which renders it an orthogonal perspective or an orthogonal setting for the two vectors together. So they are perpendicular based on that.